Hi everyone. My name is Alejandro Andrade. I'm a doctoral candidate in the Learning Sciences program at Indiana University. And I will be presenting my talk about understanding learning trajectories using multimodal learning analytics within an embodied simulation. In particular, I will be talking about the relationship between design research and learning analytics. And I think that we can use learning analytics and the data-driven models stemming from learning analytics to leverage design research. So briefly, design research is a methodological framework for the iterative production, testing, and refinement of learning environments that can actually reveal a lot of information about learning and teaching. So in a nutshell, design research starts from a theory of learning and poses some high-level conjectures for developing a set of design principles. From those design principles, you create your learning technology. And this is where I think in the next step, learning analytics kicks in by providing this data-driven model that can serve to empirically test the theory. So from the model, from this data-driven model, we can test or pose new theoretical conjectures and also pose or test embodied conjectures about the design principles. And I'm going to illustrate this framework using my dissertation data from an embodied simulation of predation dynamics. So we want to teach students the concept of unstable equilibrium, which is very important in science. It's a cross-cutting concept, and it describes the relationship between two populations. For instance, in a predation ecosystem of foxes and rabbits, those two populations change over time in a way that they describe this cyclical pattern, produce negative feedback loops, also positive feedback loops, and those changes are non-linear, as the rate of change in those populations also change over time. So this is a very complex concept, and students struggle learning it and understanding it deeply. So we're looking at a theory of learning called embodiment theory, and it states that knowing and learning is grounded in perceptual and motor cognitive processes. So the embodied learning hypothesis states that if we increase students' movement repertoires, we can support learning. For instance, if we elicit some kind of movement, and that movement maps onto the dynamic aspects of the concepts, we can support that learning. Students will ground their understanding on those dynamic aspects. The embodied learning hypothesis, furthermore, poses that this movement training will leave some traces in the students' cognition, and we're going to call that embodied representations. So the design research we are working on poses that our theory of learning is embodied cognition, and our high-level conjecture is that we can use physical movement to leverage the learning of unstable equilibrium. So we created this embodied simulation of predation dynamics. And this is a snapshot of the simulation. And on the top level, you see the display. This is what the student is seeing. On the bottom, that's what the computer is seeing. So the computer tracks students' hand position and also head pose and gaze. The student is looking at this bar chart on the left, and those population sizes correspond to the student's hands. So the computer is tracking these color blobs to create the population sizes. The student is looking, so the objective is to map the population size to those horizontal marks which are moving. So the student will map that motion, trying to um, shadow the marker's movement. As they do this, on the right-hand side, the simulation displays a line graph to trace the population changes over time. So here is a short excerpt of what the simulation does. As you can see, the student is moving their hands in order to match those horizontal bars. And it's a little bit complicated because both hands have to match those population sizes. And on the right-hand side, it's also receiving that information about the changes over time. So we pose some questions. To what extent does this embodied simulation support the learning of unstable equilibrium? To what extent does training with this embodied simulation leave traces of these embodied representations in students' cognition? Also, to what extent are learning gains associated with movement training? And this is in particular where we use learning analytics. So we had 15 third and fourth graders use the simulation. And we asked some questions, some scenarios about ecosystems before and after the embodied tutorial in individual task-based interviews. And they took approximately 30 minutes in average. So does this embodied simulation help students engage with unstable equilibrium more deeply? In analyzing the pre-post tests, which have this form, so they're short scenarios, simple scenarios, where there is a predation relationship. For instance, in this case is dolphins and fish. And we ask the students to predict what will happen in over periods of time. We scored students' answers using a learning progression coding scheme and found that the post-test is significantly higher, indicating that the simulation helped the students reorient their attention to this process and dynamic changes in these simple scenarios. Also, in order to really find evidence about these embodied representations, we look at the post-interviews and trying to find some evidence. And we looked at gestures and the way that students use gestures as semiotic resources to talk about dynamic, unstable equilibrium. So these gestures that the students produced were congruent with the elicited movement and convey action information. Furthermore, what was really interesting is that students who gestured in the post-test tended to be associated with better learning gains. So here is a short excerpt of a student's answer about the question, how many, in the dolphin fish scenario, of how many fish will be there in a month from now. Oh.
I think the fish population will go down because there will be more food and the dolphins will go up. And it's like the thing.
Great. And why is it going there?
Because when the dolphins go up, the fish go down because there's so many dolphins. But then the dolphins go down because there's not enough fish, just waves.
Okay.
Like a circle.
Well, that's true. Great. So I think the student is giving us a very rich answer. She's talking about negative feedback loops. As the predator population goes up, the prey population goes down. She also talks about positive feedback loops from the decrease in prey is going to also affect the predator population going down. And also she talks about iteration as this process is cyclical and repeats over time. So we wanted to in a way, look under the hood and see how the students were interacting with the simulation. And remember, we're training this physical movement, and we wanted to see how this movement might be associated with learning of unstable equilibrium. So we think about developing a measure of sensory motor coordination. And we're defining sensory motor coordination in this context as the ability to enact the elicited movement. So we have this perfect harmonic pattern that we are feeding the students, and they're producing their own movement, trying to reproduce the elicited one. So we looked at the computer logs of the hands positions and transformed them into direction vectors, looking in between frames, video frames, because the model that we were envisioning was the combination of hand movement as being meaningful. So for instance, at certain points in the sequence, the students were moving their hands in opposite directions, or they're moving one hand while the other is static, and conversely. So we ran a hidden Markov model to develop this sequence of latent states, where the latent states reproduce the combination of the hands movement. It will also reduce the dimensionality of the data. But what we were after was looking at the distance between the enacted movement and the elicited one. So how well the students were able to reproduce the movement. So we used an optimal matching algorithm that accounts for the temporality and sort of like measures the number of steps to transform, in this case, the enacted movement, the student movement, into the elicited movement. And we produce one value per student, and that value represented the students' sensory motor coordination. With these values, we asked ourselves whether there were patterns in which the students were interacting with the simulation. So we ran a hierarchical cluster analysis in order to find if there is kind of like natural groupings in this data. And we find that likely there is 5 groups or 5 clusters in the ways that the students interacting with the simulation. Especially, I'm going to talk about cluster 3 and cluster 4 because they revealed sort of like basic, or not basic, more clear movement. So the students' movement were more clear. And cluster 3, as you see, it has more blue lines, and those lines represent when the students' hands were static, whereas cluster 4 reveals sort of like a more fluid movement, trying to match the elicited movement. In order to understand the meaning of this sensory motor coordination, we looked at how the students responded to the questions, sort of like the association between the students' understanding and their sensory motor coordination. In particular, cluster 4 has a better initial understanding. So they are entering the simulation with a good understanding of what an unstable equilibrium might look like. And on its turn, cluster 3 students had the better learning gains. So we see that there is a pattern between how much you know about a concept and then how to recreate it in sort of like this physical representation. And also that the students in cluster 3 were sort of like stopping more often than other students might have indicated that they paid more attention to how to reproduce the movement. And that might respond to the better learning gains overall. We looked in a very exploratory way to the way that these students were looking at the 2 graphs, at the bar graphs and the line graphs. So this is these heat maps about their gaze. And as I tell you, it's very exploratory at this level. And using the movement clusters, we see that these students who didn't create a very nice fluid movement had a very restricted area of gaze, whereas cluster 3 and 4 seem to sort of like focus their attention or anchor their attention at a certain point on the graph. We don't know what's going on with cluster 5, and this is, again, very exploratory that we will look in further iterations of the project. So we have our design research, and we constructed our data-driven model of enacted elicited movement, so the distance between those two movements. Our theoretical conjecture shows that physical movement, so there seems to be an association between physical movement and learning gains. And also as an embodied conjecture about our design principles, because there is such an association, for future iterations, we think that we can create an adaptive sequence, sort of like a better way to deliver the instructions and help students really pay attention to those movements and reproduce the movement more properly so that they can map their understanding better to this unstable equilibrium. So in summary, we think we validated and tested a design that elicits as well as measures physical movement for embodied learning. And this data-driven model portrays a high-resolution picture of the learning process. Our next steps are going to look into incorporating new sensing technology to capture a larger range of physical movements using the Kinect and Leap motion. And we're also thinking about some classroom activities and how to support this in the classroom. Also, we're thinking about incorporating some game elements to tap into students' motivation by giving them scores to really pay more attention, more close attention to how to reproduce the movement. Thank you.
Okay, we got 5 minutes for questions, please.
Well, I've got two questions. The first is left and right-handed. Was any relationship with hospitals and that sort of from the students in the hand?
That's a good question, whether the students were left or right-handed, but we didn't ask them. So I don't know if that is going to influence their results. They have to use their both hands. Sometimes they used one hand only, and then the other hand, and then both hands. Sorry. So it might influence something, but I don't know how. Do you have any ideas on how it might affect their engagement?
Well, I have two dyslexic sons, and that the dyslexia can be expressed in that sort of way. So I was curious from personal perspective if there's some evidence of dyslexia in clusters.
Yeah, that's a good idea. And maybe this way of learning might not be for every learner. And maybe those learners that didn't learn much was not because they weren't able to learn about unstable equilibrium, but they weren't able to really express themselves or engage in the way that we expected from the design.
Yeah, thank you. It was a great presentation. I had a quick question. Sorry if I missed this. Could you separate the actual movement effects from the actual visualization effects? Did you have a control group where they didn't actually move, but could see the visualization?
That's what we're going to do in the next iteration. This is the first stages. So we didn't have a control group. Our sample size was small, so it's design research. But yes, we can't make causal claims. Like, it's the embodiment that really make them learn better. all we can say is that it seems that they seem to reorient their answers to be more dynamic, but we don't know if it's the movement or looking at the graphs. I don't know if you noticed, it was not that subtle, but when the student was answering the question, she didn't just did this. She sort of like implied with her hands this linear movement or this time movement. So we didn't cue that. So maybe it's incorporating that visual aspect as well.
For your the link feature extraction, did you consider using neural network? And like, why did you decide to use the model?
We use the hidden Markov model for for two reasons. To reduce the dimensionality of the data, so we just had one value, which is this latent state. And the second one, to account for the temporality in the data, sort of like producing this latent model that accounts for what's happened previously, sort of like in Markov sense. But yeah, I don't know if you have some ideas on how to account for temporality with neural networks.
I think the LSTM neural networks is a type of recurrent network. They seem to be able to calculate.
Great. So yeah, we might look into that. Yeah, like whether English learners, so is your question related, for instance, English learners might benefit from cultural backgrounds? Well, it's a very homogeneous population in Indiana, so most of our students were white, and I'm interested in looking whether we can support also learners that need to express more physically in order to convey their ideas. But one of the things that we haven't looked into cultural differences, for instance. I think those things will influence. There's personalities or ways of talking, and some people use more gestures than others. But we didn't look at any gesture. We looked at gestures that convey the action information, that convey the elicited movement. So even if I like to gesticulate a lot while I talk, we didn't look at those gestures. It was related to how they're conveying the negative feedback loops or the non-linearity in the process. So if you're more oriented towards like embodiment or movement, as some kids might be, I think they might have expressed it in gesture, or they were more likely to express it in gestures. So yeah, that's something that we may need to look in the future to control for, especially with larger sample sizes. But yeah, I like that question. There was another question here.
Yes, this is just so I can understand your research a bit better. You use cluster analysis. I'm trying to understand why that's a good idea. So you had an optimal matching score, and you had a gain score. And you could have looked just directly at the relationship between those two variables. I'm guessing that it would have been kind of a U-shaped curve because, as you pointed out, people who already had high prior knowledge wouldn't have gained as much. So if you just eliminated the high prior knowledge group, couldn't you have directly looked at those two variables and you would have seen a function? And so how would the cluster analysis give you more information or help tell us more about both?
That's a great question, and we really considering just the simple plain correlation between the similarity values and learning scores. That's what you're aiming at. We did run it and found a very, very low correlation. So I'm trying to refine the analysis. Maybe also it's a very small sample size. And that's something that I'm actually currently looking at, what's going on there. That's a great question. So
Just eliminating the people who already have high prior knowledge might help.
right, oh, thank you. Yes, that may work.
So then, building on that question, can you use hidden marker model outcomes to predict the future behavior instead of classifying them using HCA?
We could also look into that. Yes.
Quick question. In addition to cognitive outcomes, did you also look at the experience? Like maybe with traditional methods, it's the same cognitive outcomes, but maybe the students got very excited and enjoyed moments.
That's a great question. We want to look into affect. One of the features that we just got as a bonus by using the software that we're using is facial expression, facial action units actually, and see if there is something there, if there is some patterns in the way that students interacted with the simulation. By just asking the students after playing with the computer, many of them said like it was super cool. So they just like doing that because it's different. So but maybe it's just like the initial, it's a new thing to try. But the facial action units can tell us something about during the interaction if they were sort of like having issues and didn't like what they were doing or that kind of stuff.
The video of the little girl, she's explaining this
Yeah.
what happened before that? I wasn't clear. She had seen the simulation and she had done this.
That was, yes. This is the post test. Yeah.
Has she done anything else? What was it that she did that brought her to that stage?
So this was part of a science unit, and we conducted this as the pre-test. So the whole initial scenario question, the embodied simulation or the embodied tutorial, and then post-test or post-scenario happened in half an hour during the initial days of the science unit. So I don't know the initial scores, like the pre-test score for this particular student.
The activity was just watching the simulation and doing this.
Yes, that was the tutorial. That was what she did.
So then in the video, she is doing this again. Now she's explaining to you when more population goes up, the other goes down.
Mm-hmm.
That's basically what she did. Yeah.
Mm-hmm.
And was she told that this is the population is rise and fall, or did she read that from the graph?
Oh, I see. Yes. So I forgot to mention that what we do in the tutorial is to ask questions to reflect upon the movement, and also before the next task to predict what's going to happen. So we're talking about foxes and rabbits, and the first scenario was about I think it was foxes and rabbits, and then they go to the dolphins and fish, and that's maybe why the vocabulary it's very right on. Yeah, thank you for
Okay,
your
thank you very
comment.
much.